Welcome to our differential equations course. This first video is going to introduce differential equations and ultimately answer the question about what is differential equations. Well, a simple definition of differential equations would be some type of equation containing the derivatives of one or more unknown functions. And in a course about differential equations, we generally have one simple goal, and that goal is to find the unknown function. When you took algebra classes, your goal was to find the unknown variable, or the values. You had equations like x plus 3 equals 7, and by applying skills of algebra, you found out x equals 4. Well, now in differential equations, we're going to have an equation containing derivatives of a function. Maybe the second derivative of y minus 4 times the first derivative of y plus 3 times y equals 0. And over our study of this course in differential equations, we're going to find ways to find solutions, such as y equals e to the x plus e to the 3x. And it turns out this y equals e to the x plus e to the 3x function is the unknown function that makes the first original function a true statement. And I should note that this is only one possible solution, because we're going to find out there's a whole family of solutions that can satisfy this differential equation. But before we get too far into solving differential equations, we're going to hit a little bit of vocabulary around differential equations. There's two general types of differential equations that we'll work with. In this course, we're going to focus on what are called ordinary differential equations. And ordinary differential equations have a single independent variable. An example of an ordinary differential equation would be dy dx plus 5y equals e to the x. It's got a single independent variable of x. In more advanced classes, you might take a course on partial differential equations. And in partial differential equations, we have multiple independent variables. An example of a partial differential equation would use partial derivatives. You'd see the partial of z with respect to x plus the partial of z with respect to y equals 0. And now we have x and y as two independent variables in this partial differential equation. Another way we classify differential equations is based on their order, or the highest derivative in the problem. For example, if we have y prime prime plus 2y prime plus 5 equals 0, you'll notice we've got two primes, or a second derivative in here. So we would call this a second order differential equation. Another example, if we had the third derivative of y with respect to x minus 2 times the second derivative of y with respect to x plus 4x times the first derivative of y with respect to x is equal to tangent of x. Lots going on there, but what's important is we're talking about a third derivative, so we would call this a third order differential equation. Another way we can classify differential equations is based on their linearity. Just like with algebra, linear functions were the most easiest to work with. We'll find similar things happen with differential equations. If a differential equation is linear, a simple definition of linear would be that the y's are only y's. Only y, y prime, maybe y prime prime, etc. There's no exponents, there's no products, there's no functions of y's. The y's stand alone. So, for example, a linear function might be y prime prime minus 2y prime plus y equals the cosine of x. Because the y's are not multiplied by anything, there's no exponents on the y's, there's no functions of y's, this is linear in terms of y. Another example might be x cubed dy dx plus e to the xy equals 3. Again, you notice the derivatives of y and y stand alone. Contrast this with non-linear functions. Maybe an example of a nonlinear function might be y times y prime plus 2y equals e to the x. And because we have this y times y prime, we've got a product involving y's or its derivatives. This is considered a non-linear differential equation. Another example might be the second derivative of y with respect to x plus the sine of y equals 0. Well, again, this one has a sine of y. It's got a function of y, which is going to make it not a linear function. One more example. If I have xy prime minus y squared equals e to the x, here you notice we've got a power on y, which makes it not a linear function. All right, now that we've taken a look at differential equations, what they are, and how we can classify them, let's look at a way that we can verify a solution to a differential equation. It is claimed that y equals x e to the x is a solution to the differential equation y prime prime minus 2y prime plus y equals 0. Well, to verify it's a solution, just like in algebra, we want to plug this solution into the equation. First, though, we have to find all the derivatives that the equation calls for. You'll see it has a second derivative, so we're going to calculate the first and second derivatives of y so we can plug them in. We have a product rule, so we take the derivative of the first times the second plus the derivative of the second times the first to get e to the x plus x e to the x. For the second derivative, the derivative of e to the x, plus we've got that same product rule. It's going to give us another e to the x plus x e to the x. And we might even combine like terms to call it 2 e to the x plus x e to the x. Now we're ready to plug this in to see if it's really a solution to our function. Y double prime is going to be equal to 2 e to the x plus x e to the x minus 2 y prime, which is e to the x plus x e to the x, plus y And the original y given to us was x e to the x. We hope this equals 0 when we simplify it. Let's see what happens. Distributing the negative 2 through, we get 2e to the x plus x e to the x minus 2e to the x minus 2x e to the x plus x e to the x. And then if we combine like terms, we have 2e to the x minus 2e to the x is 0. X e to the x minus 2x e to the x plus x e to the x also equals 0, which is what the differential equation needed to equal. So we have verified that y equals x e to the x is a solution to our differential equation. Now, I mentioned earlier that this is one solution. Solutions often come in a family of solutions. So, for example, it could be claimed that y equals some constant times the cosine of 4x plus another constant times the sine of 4x is a solution to the differential equation y double prime plus 16y equals 0. We'll do much the same thing. We're just going to this time have constants that are going to float around in our answers. The derivative of cosine is negative sine. Using the chain rule, we've got negative 4c1 sine of 4x plus, again using the chain rule, 4c2 cosine of 4x. And then y double prime, using the chain rule again, we've got negative 16 c1 cosine of 4x minus 16 c2 sine of 4x. What happens when we plug it into our differential equation? Well, y double prime is equal to negative 16 c1 cosine of 4x minus 16 c2 sine of 4x plus 16y. Y is c1 cosine of 4x plus c2 sine of 4x. And we hope that this is going to equal 0. Well, distributing the 16 through, we get negative 16 c1 cosine 4x minus 16 c2 sine of 4x plus 16 c1 cosine 4x plus 16 c2 sine of 4x. And we can see then combining like terms on the cosine and the sine gives us 0, which is what we were hoping for. And so we've shown that this family of solutions is a solution to this differential equation. I could pick any constant c1 and c2, and it would be a solution to this differential equation. All right, in this video, we've taken an introductory look at differential equations. We've looked at some vocabulary and how we can classify differential equations and how to verify a solution is in fact a solution to a differential equation. Now it's your turn to practice. Good luck as you try the homework problems.